In this video, we're going to start looking at some of the ways that we use the integration rule for natural log functions. Yesterday, we looked at the derivative of log functions, and we saw that if we take the derivative with respect to x of the natural log of x, we get 1 over x. Now, the other thing that is important to keep in mind, I don't know if you can hear that, my dogs are wrestling in the background. The other thing that you want to keep in mind is that the domain of the natural log of function, the natural log of x function, is 0 to infinity. So you cannot take the log of 0, you cannot take the log of a negative. So that's why we have to keep it positive numbers only. That is important when we look at our integration rules. So we're going to be working backwards from this value. What we're looking at is not what the antiderivative of natural log of x is, but when is the antiderivative going to equal the natural log? Well, that would make sense if we work backwards from the derivative rule we learned yesterday. If we take the integral, the antiderivative of 1 over x dx, then what we get is the natural log of the absolute value of x plus c. And we must have the absolute value, again, because of this domain restriction on natural log. If we have 1 over negative 2, that's not going to work when we turn it back to a log. So that is why we have to place that restriction on x. Okay, don't forget your plus c's when we're doing just regular antiderivatives. If it's a definite integral, then you'll evaluate it, you'll get a number. But the antiderivatives, you're going to need that. Now, the second one is looking at u substitution. You are going to have to use u substitution some way, somehow, in a lot of cases, most of the time, okay? Because it's very rare that you're just going to have the antiderivative of 1 over x. Okay, let's use those rules to do the first few examples in these notes. So the first one, is the natural log, the antiderivative of 1 over x to the 5th. Now, this is not 1 over x, so we have to use u substitution. So remember, we're always looking for the inside and the outside. When you have a u substitution where it's going to end up being a log, you're always going to choose the denominator to be the u, because that's what we want. We want it to be over u. So let's let u equal x minus 5. And if that's the case, then du is going to be equal to 1 dx. Well, that's an easy substitution. Now our integral becomes 1 over u du, which is equal to the natural log of the absolute value of u plus c. And now we put our u's back. So this is the natural log of the absolute value of x minus 5 plus c. The end. Okay, let's look at the next one. Now, there's not like an inside and an outside like some of the ones we've seen before. So we're going to go ahead and use the whole denominator as our u. So u is going to be 3 minus x cubed. That makes du negative 3x squared dx. Now, again, we have to adjust for this negative 3 value. So basically what we do is we multiply by negative 3, which means we have to multiply by negative 1/3 outside to balance it out. So when we set this up in terms of u, I'm going to have negative 1/3 times the absolute value of 1 over u, I keep saying absolute value, the antiderivative of 1 over u du, which is equal to negative 1/3 times the natural log of the absolute value of u plus c. And now we'll put our x's back in, and so we get negative 1/3 times the natural log of the absolute value of 3 minus x squared plus c. The end. All right. Okay, now let's look at number 3 and number 4. These are not always going to require the log rule. Some of them might, some of them might not. So if I look at 3, I feel like the inside is not going to be the whole denominator. The inside to me seems like the inside of this radical. So that's what I'm going to choose for u. I'm going to let u equal 9 minus x squared. That makes du equal to negative 2x dx. Whoops. And that looks like that's going to work out with what we have. Okay, I'm going to need to, again, adjust with a negative 2 in here and a negative 1/2 out here. You can do that step in your head. You don't have to write it down. So in terms of u, we're going to get negative 1/2 times the antiderivative of 1 over the square root of u du. And you can see now that we've put that in, this is not a log rule. This is the power rule because this is negative 1/2 times the antiderivative of u to the negative 1/2 du. So we just use our power rule. We have the negative 1/2 times, add 1 to the exponent, that's positive 1/2, divide by the new exponent, that makes it times 2, and then plus c. So we can do two things here. We can see that these are going to divide out, and now we can go ahead and put our u back in. So we get negative 9 minus x squared to the 1/2 plus c. You could write square root instead of 1/2. That's fine. Now, what I really want you to notice on this one is I don't want you to all of a sudden now start turning all fractions into natural logs. These are going to be u substitution just like anything else, but remember what we've seen before is that the power rule breaks down. The power rule for antiderivatives has that caveat that if you have, like, I don't remember what they called it, u to the n power, the antiderivative, du. The caveat is that n cannot equal negative 1. That's where the power rule falls apart because you end up dividing by 0. That's where the natural log comes into play. So you're going to choose insides and outsides and u's and du's the exact same way we always have done before. But what this integration rule does is it allows you to take care of that case where the power rule fails. Okay? So if we look at number 4, there's a couple of different options of how we could set up u. We could choose u to be the whole denominator, x natural log of x squared. But I notice that's going to have a power rule in it. So that's going to be a really complicated du, and there's no way that's going to match what I have in my integral. So maybe I could choose to let u be x squared because that's inside the natural log. Now I'll warn you, that doesn't work either, so don't write that down. But here's how I know that doesn't work. If I let u equal x squared, then du equals 2x dx. That seems like it's going to work. So what this would look like with u substitution, I need to put, well, here's why this is a problem. This is 2x dx. This is all over 1. So these things have to be in the numerator. They are not. I have an x in the denominator. That's not going to do me any good. I need to do something where when I do my du, I'm going to get that x in the denominator, which is why I'm now going to choose to let u, and this is the correct way, u be the natural log of x squared. Okay. When I do that, my du is going to be 1 over x squared times 2x dx, which means we get 2 over x dx. Now, the dx is in the top because that's over 1. But now the x is in the denominator, which is what we want. So again, we have to adjust. We need a 2 and a 1/2. So when we do our u substitution, this is going to be now 1/2 times, oh, that wrote weird, the antiderivative of, here's where I have my 2 over x dx. So all of that gets to take du. I have 1 over u du. Remember that this piece alone was our u. So there's the 1 over u. All the stuff in green is our du. So we get 1/2 the natural log of the absolute value of u plus c. And the final answer is going to be the natural log of the absolute value of the natural log of x squared plus c. This is weird looking with the log inside the absolute value, but it's totally valid. Okay. All right. Pause the video and try 5 and 6 so that you can see how you're doing. See if you can decide what u and du should be at the very least. And then come back in just a couple of seconds and we'll talk through the answer. But go ahead and put it on pause so you can take a second to try 5 and 6 on your own. So here's how I set up number 5. I let u be the inside of the parentheses there. I didn't want to distribute. So 1 plus x to the 1/3. Remember, the derivative of a constant is always going to be 0, so it's worth taking the constant when it's a part of the term there. I also knew if I took the derivative of x to the 1/3, when I subtract 1, I get 2/3. So that's kind of how I knew I didn't want to multiply out, because that was going to get me the 2/3. You get negative 2/3 really when you subtract, but that negative exponent moves the x to the 2/3 to the denominator, which is the position where we need it. So we have 1 over x to the 2/3 dx. That is what we need for du, with the exception of the 2/3. So we also have to multiply by 3/2. I did them both on the outside because I was out of room. But that's basically how we're going to get what we want. So this is going to come out to 3/2 times the antiderivative of 1 over u du, and you can finish the rest from there. All right. Let's look at this last one real quick. Now, I will warn you, I'm just going to show you this last one because if you messed around with the u and du for a little bit, you would find it is not working. This one is really kind of a puzzle. And so I just want to kind of show you it because it's another strategy you can keep in your back pocket. We have not had to do this before, but I would also say that this is not common at all. And this is probably a little outside of the realm of what I would personally ask you to do, but it is kind of a cool thing to know. So in this case, like the only real option that kind of makes sense, I think, is to just let u be the denominator. And if you played around with this, you probably tried all kinds of different things and weren't really getting anywhere. So I'm going to let u be the denominator. Then du becomes 1/2 times 2x to the negative 1/2 times 2, dx. And that's all using chain rule right there. So these 2's divide out, and it turns out that du is equal to 1 over the square root of 2x dx. And this is where I get totally stumped, because I can see the 1 over u that we're going to get, but I don't know what to do with that du, okay? And so then I thought to myself, well, we've seen where we sometimes have to solve for u instead or rearrange to solve for x instead. And that didn't really get me anywhere. And then I thought, well, I don't have any x's in there, but I do have 1's. So I thought, what if I solve this for 1? That means that 1 is equal to u minus the square root of 2x. Just subtract square root of 2x from both sides. And I thought, well, that didn't do me any good because now I have u's and x's mixed together. I don't want that. So we don't want to do that. So then I thought, well, but at least I could get the x's by themselves. So I had u minus 1 equals the square root of 2x. And I could square both sides and divide by 2, but there's nowhere that I can substitute that in. We don't even have another x. But then I noticed that there's a square root of 2x here. There's also a square root of 2x here in my du. So here's where this gets a little bit weird. We're going to also rearrange this guy. So instead of having it solved for du, I'm going to have it be solved for dx. And if I multiply by the square root of 2x on both sides, I find out that dx is equal to the square root of 2x times, sorry, that scared me so bad. My dogs just barked at something. I'm sorry. And I'm not going to re-record this, so you all get to hear me scream on this video. All right. Where was I? I got distracted. So now we have that dx is equal to the square root of 2 times du, which is still not any good because that has x's and u's mixed together, except for the fact that I know what the square root of 2x is in terms of u. Therefore, dx is equal to u minus 1 du. And if that doesn't just rock your worlds, I don't know what does. That's fair game. And like I said, is that something that I would have expected you to see on your own? No, but it's worth looking at because it's kind of interesting and it's a strategy that we haven't had to use before. You can always substitute for dx instead of du as long as dx is solved for by itself. So now let's put this together. I know that the u substitution I did makes this 1 over u, but then dx is equal to u minus 1 du. Now we can distribute this 1 over u, and that gives us the antiderivative of 1 minus 1 over u du, and that we can certainly do. I'm sorry. Dumb dog, sorry. Okay, now when we take this antiderivative, we get the antiderivative of 1 is u minus the natural log of the absolute value of u, that's this piece, and then plus c. So your final answer, and this is the weirdest one that we've seen so far this year, is going to be u, which is 1 plus the square root of 2x, minus the natural log of the absolute value of 1 plus the square root of 2x, and then plus c. That's like a level 10 kind of integral there. But that is just another thing to add into your toolbox to help you be prepared when you see weird stuff come up. So go ahead and get started on worksheet 2 today. You should be able to do quite a few of them. When you get to some of the tougher ones, just hang tight and we'll go over those when I see you next. See you later.